The Hwacha rocket launcher. In 1592, during the Japanese invasions of Korea, defenders stationed atop the walls of Jinju Fortress prepared a device that looked more like a wooden cart than a weapon of war. The air was thick with smoke from burning villages in the distance. Japanese infantry advanced in tight formation, shields raised, confident in their numerical superiority. Then, without warning, a rectangular frame tilted forward. Hundreds of flaming projectiles erupted into the night sky in a single coordinated discharge. The device was known as the Hwacha, first formally documented in 1409 under the reign of King Taizong of the Joseon dynasty. At first glance, it appeared simple, a wooden cart mounted with a board perforated by rows of cylindrical launch tubes. But each tube held a Singajon rocket arrow, a projectile combining an arrow shaft with a gunpowder propulsion unit. Depending on the configuration, a single Hwacha could launch between 100 and 200 rockets simultaneously. The rockets measured roughly 2 to 3 feet in length and were stabilized by feathered fins. Once ignited, they could travel up to 500 feet before descending into enemy formations. Some variants carried explosive charges or incendiary tips, designed to ignite wooden shields and armor. The psychological effect alone was devastating. Contemporary accounts describe the sky filling with streaks of fire, followed by chaos among advancing troops, who had no precedent for such a barrage. Unlike traditional archery, the Hwacha did not rely on individual skill. It was a mechanical multiplication of force. A small defensive unit could unleash a wall of projectiles in seconds, effectively overwhelming larger forces. Military manuals such as the Gukjo Oryui and later the Muye Dobo Tongji detailed its construction and deployment. Archaeological reconstructions confirmed the plausibility of its firing mechanism and range. Mainstream historians categorize the Hwacha as an early form of rocket artillery, primitive compared to modern systems, but innovative for its time. It was particularly effective in defensive warfare, where enemies advanced in predictable paths toward fortress gates or narrow passes. However, its inaccuracy over longer distances and dependence on static positioning limited its battlefield versatility. Yet the contradiction remains striking. This was the 15th century. Europe had not yet developed comparable multi-rocket launch systems. Gunpowder was spreading, but coordinated rocket saturation attacks were rare outside East Asia. The Hwacha represented not merely an adaptation of gunpowder, but a strategic reimagining of projectile warfare. It transformed individual arrows into collective destruction. Despite its success during the Imjin War, the Hwacha did not evolve into increasingly advanced artillery systems within Korea. Over time, as musket technology improved and cannons became dominant, the Hwacha faded from primary military doctrine. It became a defensive relic rather than a foundation for a rocket-based arms race. If a system capable of launching hundreds of rockets in seconds existed in 1409, why did rocket artillery not become the dominant battlefield technology centuries earlier? Was it technological limitation, logistical complexity, or strategic conservatism that prevented its expansion? The Hwacha stands as evidence that the concept of saturation fire, overwhelming force through simultaneous projectile release, was understood long before the industrial age. The idea was there, the mechanism worked, the battlefield impact was real. And it raises a question that echoes through military history. How many technologies capable of reshaping warfare appeared too early, only to be quietly set aside before their full potential could unfold? The Roman Plumbata. In the 3rd century CE, as the Roman Empire faced mounting pressure from invading forces along its borders, a subtle but deadly innovation began appearing behind the shields of legionaries. Before swords clashed and before spears struck, Roman infantry would pause, reach behind their scutum shields, and release a volley of small, weighted darts. These projectiles, known as plumbatae, fell silently through the air before piercing into enemy ranks. At first glance, the plumbata seemed modest. Each dart measured roughly 12 to 18 inches in length. A slender wooden shaft supported iron fletching at one end and a sharply pointed metal tip at the other. Around the shaft near the head sat a heavy lead weight, plumbum in Latin, giving the weapon both its name and its unusual aerodynamic force. That added mass allowed the dart to arc higher and strike harder than a standard javelin of similar size. Unlike the large pilum spear traditionally thrown by Roman soldiers, the plumbata could be carried in multiples. Historical sources suggest each legionary might carry up to 5 darts clipped inside the hollow of the shield. When ordered, entire ranks could unleash a sudden rain of lead-weighted missiles before closing in with swords. The physics behind the plumbata made it deceptively dangerous. The lead weight shifted the center of gravity forward, stabilizing its descent. When thrown in a high arc, gravity amplified the impact. Even modest throwing strength could produce penetrating force capable of breaching leather armor and wounding through mail at close range. Archaeological finds across Europe have uncovered surviving dart heads and lead weights, confirming their standardized construction. Roman military manuals, including later texts like Vigedius de Re Militari, describe the plumbata as a decisive tool capable of disrupting enemy formations. Before the opposing side could brace for melee, they would be struck from above. The tactic introduced a vertical dimension to infantry combat. Shields, designed to block forward thrusts, offered less protection against descending projectiles. Mainstream historians interpret the plumbata as an efficient adaptation during a period of military reform. As Roman legions became more flexible and defensive in strategy, portable missile weapons allowed infantry to soften enemies without relying solely on heavy artillery. Yet the plumbata raises a deeper contradiction. It was small, easy to manufacture, and highly effective. It required no complex machinery. It could be mass-produced and deployed instantly. In many ways, it represented the ideal infantry support weapon, and yet, over time, it faded from widespread use. Records of plumbatae become increasingly scarce after the late Roman period. While similar darts appeared in various cultures, the systematic Roman deployment diminished. Unlike siege engines or large-scale artillery, the plumbata did not evolve into increasingly advanced descendants. Why would an army abandon a weapon that multiplied the lethality of each soldier without adding significant burden? Some scholars argue that changing armor designs reduced its effectiveness. Others suggest evolving battlefield formations made the tactic less practical, but none of these explanations fully account for its disappearance. The plumbata stands as evidence that battlefield innovation does not always follow a linear path. Sometimes a weapon emerges that solves a tactical problem perfectly for a specific era, only to vanish when that era ends. And it leaves behind a question that lingers quietly. How many effective technologies were lost, not because they failed, but because the world around them changed too quickly for them to adapt? The Indian Urumi flexible sword. In the 12th century, deep in the southern regions of the Indian subcontinent, warriors trained with a weapon that defied conventional expectations of what a sword should be. Instead of a rigid blade, they wielded a strip of flexible steel, sometimes as thin as a belt, sometimes extending over 5 feet in length. When coiled at the warrior's waist, it appeared harmless. But once unfurled and set into motion, it transformed into a whirling arc of sharpened metal. This was the Urumi. Forged from high-carbon steel, the Urumi's blade was narrow and razor-sharp along its edges. Unlike traditional swords that relied on thrusting or slashing in controlled arcs, the Urumi required continuous circular motion to remain effective. The wielder would spin the weapon around the body, maintaining momentum so the flexible blade extended outward through centrifugal force. At full speed, the rotating steel created a lethal perimeter several feet in diameter. Historical accounts from the Kerala region associate the Urumi with the martial art of Kalaripayattu, one of the oldest known combat systems in the world. Training with the weapon was restricted to advanced practitioners because its operation demanded extreme precision. A momentary lapse in rhythm could cause the blade to recoil unpredictably. In enclosed spaces or tightly packed formations, the risk of striking allies was significant. The design was both ingenious and volatile. Its flexibility allowed it to bypass shields and entangle opponents' weapons. A conventional block might not stop it, as the blade could curve around defensive structures. Some versions featured multiple parallel blades attached to a single hilt, multiplying its cutting potential. Each additional strip increased both its lethality and its danger. From a materials perspective, forging such a weapon required metallurgical expertise. The steel had to be thin enough to bend without breaking, yet strong enough to maintain an edge. Surviving specimens and later reproductions confirmed the feasibility of the design. modern demonstrations reveal that even controlled practice demands substantial open space and coordination. Mainstream historians often frame the Urumi as a ceremonial or specialist weapon rather than a primary battlefield tool. Its complexity and the high level of training required limited its scalability. In large-scale warfare, formations favored predictable, controllable weapons such as spears and straight swords. The Urumi thrived in dueling or small unit combat, where mobility and unpredictability offered advantage. Yet this explanation only partially resolves the paradox. The Urumi represented a radical departure from rigid blade doctrine. It exploited physics differently, transforming rotational energy into cutting force. It challenged the assumption that swords must be straight and solid to be effective, and for a time, it functioned within structured martial systems. Despite this, the Urumi never became widespread beyond specific regions. It did not inspire a wave of flexible blade weaponry across other civilizations. Its presence remained geographically contained, eventually transitioning into symbolic and traditional use rather than mass military adoption. Was the limitation purely practical, a matter of safety and training difficulty? Or did its unpredictability make it unsuitable for disciplined armies? A weapon that could not be easily standardized may have been too volatile for organized formations. The Urumi demonstrates that innovation in warfare is not always about increasing brute force. Sometimes it involves rethinking the fundamental mechanics of motion and control. But when innovation introduces as much risk to the wielder as to the opponent, its survival becomes uncertain. And it leaves behind a quiet, unsettling thought. How many experimental weapons proved too dangerous to institutionalize? Not because they lacked power, but because they demanded mastery few could sustain. The Scorpion bolt thrower. In 52 BCE, during Julius Caesar's campaign in Gaul, Roman forces encountered fortified settlements positioned on elevated terrain. Direct assault meant climbing slopes under a hail of enemy missiles. In response, Roman engineers deployed a compact artillery device capable of striking targets with unnerving precision. Mounted on wooden frames and braced with twisted bundles of sinew, the machine resembled an oversized crossbow. It was called the Scorpion. Unlike large siege engines designed to batter walls, the Scorpion was engineered for accuracy. Its mechanism relied on torsion power. Two vertical frames held tightly wound animal sinew ropes, twisted under extreme tension. A rigid arm sat between them, drawn back by a winch system. When released, the stored torsion energy propelled a heavy bolt forward at remarkable velocity. The bolts, often around 2 to 3 feet in length with iron heads, were capable of penetrating shields and even certain types of armor. Positioned along ramparts or within fortified camps, the Scorpion allowed Roman units to eliminate enemy archers, commanders, or expose soldiers at distances that exceeded most handheld weapons. Archaeological reconstructions suggest effective ranges of up to 300 yards under optimal conditions. Roman military treatises, including descriptions attributed to Vitruvius and later technical manuals, detail the calibration required to maintain torsion balance. The sinew bundles had to be kept at specific moisture levels to preserve elasticity. Too dry, and they became brittle. Too damp, and tension weakened. The engineering sophistication required constant maintenance and trained operators. Mainstream historians interpret the Scorpion as a natural development within Roman siege doctrine. It bridged the gap between handheld missile weapons and massive artillery like ballistae. Its portability made it adaptable across different terrains. Yet, what distinguishes the Scorpion is not merely its mechanics, but its tactical implication. For the first time in many battle contexts, a relatively small crew could selectively remove high-value targets from considerable distance. A commander surveying the field could be struck before issuing orders. An archer atop a wall could fall without warning. The Scorpion introduced a form of battlefield precision that resembled targeted elimination more than chaotic melee. Despite its effectiveness, the Scorpion did not become a universally dominant weapon across subsequent centuries. While similar torsion devices persisted, the Roman system of widespread deployment diminished as military structures evolved. The reliance on specialized crews, maintenance demands, and logistical complexity may have limited its scalability. Yet there remains a contradiction. If precision artillery capable of decisive strikes existed in the 1st century BCE, Why did the concept of long-range targeted elimination not accelerate more dramatically? The principles were understood, the mechanical knowledge was present, the battlefield value was proven. Perhaps the answer lies not in technological limitation, but in strategic philosophy. Warfare of the era often centered on formation, strength, and direct confrontation. Precision elimination may have disrupted established codes of engagement in ways not fully embraced. The scorpion stands as a reminder that the idea of distant controlled lethality is ancient. Long before firearms dominated, engineers were already manipulating stored energy to project force with surgical intent. And it invites a deeper question. If the tools for targeted warfare existed over 2,000 years ago, how different might military history have unfolded had those tools been refined without interruption? The Chinese fire lance. In the early 10th century, along the shifting frontiers of the Song dynasty, infantry units carried what appeared to be reinforced bamboo spears. At first glance, they resembled traditional polearms used for thrusting in close combat. But attached near the blade was a hollow tube packed tightly with gunpowder. When ignited, the tube did not simply flare, it erupted. The weapon was known as the fire lance. Initially developed during the late Tang and early Song periods, it represents one of the earliest documented combinations of gunpowder propulsion and handheld weaponry. Unlike rockets, which launched independently, the fire lance remained connected to its wielder. The operator would brace the spear, ignite a fuse, and direct the tube toward advancing enemies. For several seconds, a concentrated jet of flame and sparks blasted forward. Early versions primarily projected fire. However, written records from the Wujing Zongyao and later Song military compilations describe modifications that included shards of pottery, iron pellets, or metal fragments packed within the tube. When ignited, these fragments were expelled along with the flame, transforming the fire lance from a psychological deterrent into a short-range explosive projectile device. The tube typically measured around 12 to 18 inches in length. Gunpowder mixtures varied, but the proportions evolved as alchemical experimentation improved combustion efficiency. The flame could extend several feet beyond the spear tip, creating a sudden wall of heat and shrapnel. In tight formations, especially during siege defense or gate protection, the effect was both disorienting and destructive. Mainstream historians recognize the fire lance as a transitional weapon, a bridge between incendiary devices and the earliest true firearms. Over time, as metallurgy advanced, bamboo tubes were replaced with metal barrels. Eventually, projectile propulsion overtook flame projection, leading to primitive hand cannons. In this sense, the fire lance stands at the threshold of gun history. Yet the contradiction is significant. The conceptual leap from flame projector to bullet-launching firearm occurred centuries before firearms reshaped global warfare. The mechanism was there. The understanding of explosive force was documented, but widespread, reliable handheld guns did not immediately dominate battlefields worldwide. Part of the reason lies in instability. Early gunpowder compositions were inconsistent. Tubes could rupture, premature ignition could injure the operator. In close formations, a misfire risked harming allies. Unlike bows or crossbows, which required muscle and tension, the fire lance introduced volatile chemical energy into infantry ranks. There was also the matter of doctrine. Military systems often resist abrupt transformation. Traditional spear formations had centuries of refinement. Integrating explosive propulsion required new tactics, training, and logistical supply chains for powder production. Such structural shifts rarely occur overnight. Still, the fire lance altered the trajectory of weapon development. It marked the moment when combustion replaced torsion as a primary means of projectile force. The implications were immense. Within this simple tube was the blueprint for cannons, muskets, and eventually all gun-based weaponry. If a proto-firearm existed in the 10th century, what slowed its full evolution into dominant small arms? Was it technological constraint, cultural resistance, or the inherent danger of early explosive experimentation? The fire lance demonstrates that the concept of handheld explosive propulsion emerged far earlier than many assume. It was unstable, unpredictable, and revolutionary all at once. And it suggests that the path from invention to global transformation is rarely immediate, even when the spark has already been lit. The Chinese hand cannon prototype. In 1288, During the late years of the Yuan dynasty, a small bronze tube was buried beneath the chaos of frontier warfare. It was not large like a siege cannon, nor mounted on walls. It could be held in both hands. When ignited, it expelled fire, smoke, and a solid metal projectile from its narrow mouth. Archaeological evidence suggests this was one of the earliest true hand cannons ever deployed in combat. The device measured roughly 12 to 14 inches in length, cast from bronze with a thickened breech to withstand explosive force. A small touch hole at the rear allowed ignition by inserting a burning match cord. The barrel interior was smooth, lacking rifling, and designed to fire either lead balls or crude metal pellets packed with gunpowder. Surviving specimens, such as those excavated in Heilongjiang province, display irregular casting marks and uneven bore surfaces, evidence of early experimentation rather than perfected engineering. Unlike the fire lance, which primarily projected flame and fragments, the hand cannon represented a shift toward contained explosive propulsion. Instead of projecting outward from an open tube, the metal barrel confined the expanding gases, directing them forward behind a solid projectile. This was the mechanical threshold where gunpowder ceased to be merely incendiary and became ballistic. Contemporary records describe its use in defensive operations along contested borders. Infantry would brace the cannon against wooden supports or rest it on primitive stocks. When fired, the recoil was substantial. The projectile range was limited, likely under 200 feet for effective accuracy, but at close distance the impact force could penetrate light armor. Mainstream historians consider the Yuan hand cannon a transitional weapon, a bridge between explosive devices and personal firearms. It marked a decisive departure from mechanical propulsion systems like torsion engines, yet it carried inherent instability. Early gunpowder mixtures were inconsistent. Bronze casting quality varied. A structural flaw in the barrel could result in catastrophic rupture. Excavated hand cannons show thick breech walls, suggesting awareness of pressure risk. Some recovered specimens display cracks or deformation, indicating that failures did occur. Handling such a device required careful powder measurement and controlled ignition timing. Inexperienced soldiers risked premature explosion. The contradiction is striking. This was the 13th century. Europe would not widely adopt handheld firearms for decades. Yet the fundamental architecture of the gun, a metal barrel, explosive charge, projectile, was already present. The principle of directed ballistic force had emerged. Despite this breakthrough, the hand cannon did not instantly replace traditional weapons. It was heavy, slow to reload, and unreliable in wet conditions. Skilled archers could fire multiple arrows before a cannon was prepared for a second shot. Logistics required consistent powder supply and metal production capacity. If the blueprint for personal firearms existed in the 1200s, why did it take centuries for handheld guns to dominate battlefields globally? The engineering concept was proven, the explosive chemistry was understood, but institutional transformation lagged. Perhaps armies hesitated to entrust infantry with unstable explosive tubes. Perhaps production limitations restricted scale. Or perhaps, at that moment in history, the weapon was ahead of the tactical systems needed to support it. The Chinese hand cannon prototype represents more than an early gun. It represents the moment warfare crossed from mechanical tension to chemical detonation as its primary source of force. The transition was irreversible, and once explosive propulsion entered the hands of individual soldiers, the trajectory of warfare shifted permanently, even if the world did not immediately recognize it. The Persian scythe chariot. In the 5th century BCE, on the vast plains controlled by the Achaemenid Empire, war was often decided by formation discipline. Infantry stood shield to shield, spears locked forward. The strength of an army depended on cohesion. Into that wall of order thundered something designed to break it in seconds. The Persian scythe chariot was not simply a vehicle, it was engineered shock warfare. A standard 2-horse chariot was modified, with long, curved blades attached to its wheel hubs and sometimes extending horizontally from the axle. These iron scythes could stretch several feet outward, rotating at high speed as the chariot advanced. At full gallop, the spinning blades turned the entire vehicle into a moving cutting machine. Historical accounts, particularly from Greek sources describing battles against Persian forces in the 5th and 4th centuries BCE, detail the intended effect. The chariot would charge directly at dense infantry formations. The scythes, aligned roughly at shin and waist height, were designed to slice through legs, destabilize ranks, and create panic. Once gaps appeared, cavalry or follow-up infantry could exploit the disruption. Structurally, the chariot required careful balance. The additional weight of iron blades altered wheel stability and maneuverability. The driver had limited ability to adjust direction at high speed. Success depended on momentum and surprise. If infantry held formation and opened ranks at the right moment, the chariot could pass through without inflicting mass casualties. This was the core weakness. Greek military adaptations evolved quickly. Soldiers were trained to maintain discipline, step aside at the last second, and attack the exposed driver or horses once the vehicle slowed or became entangled. Without shock and panic, the scythe chariot became vulnerable. Its long blades, lethal during motion, offered little advantage once speed was lost. Mainstream historians often describe the Persian scythe chariot as an intimidation weapon as much as a physical one. Its visual impact was undeniable. A line of blade-equipped chariots accelerating toward infantry could break morale before contact. But its effectiveness relied almost entirely on psychological collapse. The contradiction is stark. The weapon was mechanically simple, yet strategically ambitious. It attempted to weaponize speed and terror simultaneously. However, its success was conditional. If the enemy stood firm, the chariot could become isolated deep within hostile ranks, easily surrounded and neutralized. Over time, as disciplined infantry formations such as the Macedonian phalanx demonstrated resilience, the scythe chariot lost relevance. After repeated failures in battles where opponents refused to panic, the tactic gradually disappeared from mainstream warfare. It proved difficult to refine. Armor improvements did not solve its vulnerability. Increasing blade length did not guarantee greater effect. The fundamental flaw remained: dependence on enemy fear. If a weapon's power collapses the moment opponents refuse to yield, psychologically, can it ever become strategically reliable? The Persian scythe chariot reveals a turning point in military thinking. It illustrates the limits of shock-based innovation. Technology alone could not compensate for disciplined counter-strategy. Once armies learned to hold formation under threat, the moving blades lost their dominance. And this leaves an open question. How many weapons throughout history were abandoned not because they lacked destructive capability, but because human discipline proved stronger than engineered terror? The Indian Qatar push dagger. In the 14th century, within the courts and battlefields of the Indian subcontinent, warriors carried a blade unlike any other. It did not extend from the hand in the traditional manner of a sword or knife. Instead, it projected forward from a pair of parallel bars gripped between the knuckles. The blade sat in alignment with the forearm, transforming the entire arm into a driving mechanism. This was the Qatar. The Qatar push dagger emerged during the late medieval period, particularly under the influence of Rajput and later Mughal martial traditions. Its design was mechanically simple, yet strategically distinct. The handle consisted of two parallel metal bars connected by cross pieces. The user inserted the fist between these bars, gripping the cross supports, while the blade extended outward from the center line of the arm. Unlike conventional daggers that rely on wrist articulation for slashing or stabbing, the Qatar was engineered for direct forward thrust. When striking, the wielder did not flick or swing. Instead, they drove the entire body weight behind the blade. The alignment allowed force from the shoulder and torso to transfer directly into the point of impact. In close combat, particularly during armored encounters, this structural advantage proved significant. Surviving examples of Qatars reveal blades ranging from 6 to 18 inches in length, often triangular or leaf-shaped to maximize penetration. Some variants featured reinforced tips, designed specifically to puncture chainmail or thin plate armor. Metallurgical studies of preserved specimens indicate high-quality steel, occasionally with pattern-welded construction, suggesting skilled craftsmanship. Historical depictions show the Qatar used in both battlefield and ceremonial duels. In tightly confined engagements, where longer swords became cumbersome, the push dagger excelled. Its compact form allowed rapid deployment and grappling range. The rigid alignment reduced the chance of the blade twisting upon impact, increasing the likelihood of deep penetration. Mainstream historians categorize the Qatar as a specialized close-quarters weapon rather than a mass infantry tool. Its effectiveness depended on proximity. Against polearms or projectile weapons, it offered limited reach. However, within controlled dueling contexts or sudden close encounters, its mechanical efficiency was undeniable. The contradiction emerges in its reputation. Some accounts suggest that certain formal duels or ritual combats discouraged or restricted the Qatar's use. The reason was not ornamental, it was practical. A thrust delivered with full body force could bypass armor defenses more effectively than many conventional blades. In encounters governed by codes of honor, a weapon capable of rapid, decisive penetration altered the balance. Yet, despite its mechanical advantage, the Qatar did not spread widely beyond the subcontinent. It remained culturally specific. Other regions developed push daggers in various forms, but none achieved the same prominence or refinement. Why would a weapon that optimized human biomechanics remain regionally contained? The concept of aligning blade and forearm to maximize force seems intuitive. Its penetration capability was documented. Its craftsmanship was reproducible. Perhaps the answer lies in doctrine. Armies prioritize range and formation. A weapon optimized for intimate distance requires scenarios where distance has already collapsed. As firearms advanced and battlefield spacing expanded, the tactical niche for push daggers narrowed. The Qatar demonstrates that innovation is not always about complexity. Sometimes it is about alignment, of steel, muscle, and intent. It refined the act of thrusting into a direct transfer of mass and momentum. And it leaves a question that lingers quietly. When a weapon makes close combat brutally efficient, does it become too decisive for systems that prefer controlled escalation? The Greek fire clay grenade. In the 10th century, within the fortified walls of Constantinople, soldiers prepared small ceramic vessels filled with a volatile liquid compound. Unlike the large siphons mounted on ships, these were handheld, compact, sealed clay containers no larger than a melon. When thrown against stone or wood, they shattered. What followed was not a simple flame, but a spreading inferno that clung to surfaces and refused to be extinguished by water. These devices were early incendiary grenades derived from the same family of substances associated with Greek fire. Byzantine military manuals and later Arab chronicles describe ceramic bombs filled with combustible mixtures, sometimes thickened with resin or oil. Once ignited and hurled into enemy formations, they burst upon impact, scattering burning liquid in multiple directions. The composition of the incendiary mixture remains debated. Theories include petroleum-based substances, sulfur, pine resin, and quicklime. What distinguishes the Greek fire compound from ordinary flame is its reported ability to continue burning even when doused with water. Some accounts describe water intensifying the reaction, suggesting chemical components that reacted violently with moisture. The clay grenade structure was deceptively simple. A thin ceramic shell enclosed the mixture, along with a small ignition mechanism, possibly a delayed fuse or pre-lit wick. Upon impact, the container fractured, dispersing the flaming substance across armor, shields, and siege equipment. In tightly packed formations, the effect could spread rapidly. Unlike arrows or bolts, which struck single targets, the clay grenade operated through adhesion. Fire attached itself to clothing and wooden surfaces. Soldiers attempting to extinguish flames often worsened the situation. Panic became as much a weapon as combustion. In siege scenarios, these grenades were thrown from ramparts onto ladders or into siege towers, turning climbing assaults into cascades of fire. Mainstream historians classify these devices as logical extensions of Byzantine incendiary expertise. The empire had already weaponized flammable compounds in naval warfare. Portable variants were a natural adaptation for land defense. Yet, the clay grenade presents a significant contradiction. It represented a form of area denial through persistent flame. The weapon did not rely solely on impact, but on chemical reaction. Its effects were difficult to contain once released. In urban environments or densely constructed fortifications, fire could spread beyond intended targets. Civilian structures were not immune. The Byzantine state guarded the composition of Greek fire with exceptional secrecy. Knowledge of its ingredients was restricted to a small circle of specialists. Over time, that knowledge vanished. No confirmed formula survives in full detail today. Why would an empire conceal and eventually lose such a powerful technology? Was it deliberate protection to prevent proliferation, or did institutional collapse erase expertise that had once been tightly controlled? The Greek fire clay grenade illustrates how chemical warfare principles existed long before modern conventions addressed them. It introduced the idea that a weapon's destructive power could extend beyond immediate physical force into sustained environmental damage. And it leaves behind a troubling reflection. When a civilization develops a weapon capable of burning beyond control, does it risk losing control of more than just the battlefield? The Indian Chakra war disc. In the 5th century BCE, across the northern regions of the Indian subcontinent, warriors trained with a weapon that appeared deceptively simple, a circular ring of sharpened steel. It had no hilt, no handle, no shaft. It's just a perfectly balanced disc, typically between 6 and 12 inches in diameter, with an outer edge honed to razor sharpness. This was the chakra. Forged from tempered steel, the chakra's design relied entirely on symmetry and rotation. The inner ring was smooth, allowing the wielder to spin it around a finger before release. When thrown, it traveled along a flat, fast-moving trajectory. Unlike a spear or arrow, the chakra did not pierce through a narrow point of impact. It sliced. The physics behind its lethality was rooted in angular momentum. Once spinning at high speed, the circular mass maintained stability mid-air. Upon contact, the sharpened circumference delivered cutting force across a wider surface area than a pointed projectile. A direct hit could sever exposed flesh or inflict deep lacerations on unarmored targets. Historical references associate the chakra with ancient Indian warfare and later with specialized warrior groups. Training required precise timing and spatial awareness. A poorly aimed throw could ricochet unpredictably. In crowded formations, misjudgment risked unintended injury. Mainstream scholarship often categorizes the chakra as a niche weapon, effective in specific contexts but unsuitable for large-scale standardized deployment. It lacked the range of bows and the penetrating force of heavy javelins, yet its compact form and speed offered tactical advantages in skirmish scenarios. The contradiction lies in its aerodynamic refinement. The concept of a balanced spinning projectile predates many later developments in rotational weaponry. The chakra demonstrated that ancient engineers understood principles of gyroscopic stability long before formal scientific articulation. Its design required knowledge of metallurgy sufficient to produce a thin, yet durable ring capable of holding an edge. Despite its effectiveness in trained hands, the chakra did not become a dominant battlefield weapon across civilizations. It remained regionally contained. As armor technology advanced and projectile weapons evolved, the open cutting edge lost some of its tactical relevance. There is also the matter of control. Unlike arrows, which follow predictable ballistic arcs, the chakra's trajectory depended heavily on release angle and spin consistency. Wind resistance and surface interaction could alter its path. Mastery required repetition, discipline, and environmental awareness. Over centuries, the chakra transitioned from battlefield application to ceremonial and symbolic presence in some traditions. Its martial prominence diminished, replaced by firearms and more standardized projectile systems. If a rotating disc capable of delivering high-speed slicing force existed in the 5th century BCE, why did rotational projectile weapons not evolve more broadly? The engineering insight was present. The metalworking capability existed, yet the concept remained isolated. Perhaps the answer lies in scalability. Weapons that demand individual mastery rarely thrive within expanding armies that require uniformity. Reliability in mass deployment often outweighs specialized brilliance. The chakra closes this investigation not as the largest or most explosive weapon, but as one that reveals how ancient civilizations experimented boldly with physics long before formal theory explained it. And it leaves behind a final reflection. When innovation emerges ahead of its supporting infrastructure, does it quietly fade, not because it failed, but because the world around it was not yet ready? Conclusion. Across centuries and civilizations, a pattern quietly repeats itself. The Hwacha unleashed saturation rocket fire centuries before modern artillery doctrine formalized the concept. The Yuan hand cannon placed explosive propulsion into the hands of individual soldiers long before firearms reshaped Europe. The Persian scythe chariot attempted to weaponize fear itself. The Greek fire-clay grenade transformed chemistry into sustained destruction. Each weapon appeared at the edge of what its era could manage. None of these inventions were accidents. They required metallurgy, engineering, tactical imagination, and organized production. Ancient militaries were not experimenting blindly. They understood leverage, combustion, aerodynamics, momentum, and psychological shock. In many cases, they reached conclusions that modern warfare would rediscover centuries later. Yet most of these weapons did not dominate permanently. Some were too unstable. Some depended on conditions that rarely aligned. Others required discipline, logistics, or institutional shifts that their societies could not fully sustain. A weapon may win battles and still lose history if it cannot integrate into a broader system. What becomes clear is that military innovation is not a straight line of constant improvement. It is uneven. Certain breakthroughs appear early, flare briefly, then recede. The knowledge exists, but adoption stalls. The idea survives in fragments, waiting for conditions to mature. This raises a deeper question about the evolution of warfare itself. How many transformative technologies surfaced long before the world was structurally ready to absorb them? How many breakthroughs were constrained not by imagination, but by the limits of infrastructure, doctrine, or political will? The narrative that ancient warfare was primitive does not withstand scrutiny. The evidence suggests something more complex. Civilizations repeatedly approached thresholds of destructive capability, then stepped back, stalled, or fractured before those capabilities could scale. Perhaps the most unsettling realization is this: technological potential often arrives before societies are prepared to manage its consequences. And when that happens, innovation does not disappear. It waits, sometimes for centuries, until the world once again becomes ready to unleash it.